We are moving towards systems that don't just generate text, but autonomously write and run self-executing code to complete multi-step tasks. This transition defines a shift toward truly autonomous AI agents. To understand the engineering challenge, consider the standard workflow of prompting a current large language model. Assigning it a massive project, like auditing a sprawling legacy codebase while simultaneously compiling a competitive market matrix, regularly results in failure. This diagram illustrates the failure. A monolithic generative AI node attempts to manage a highly complex process tree, but hallucinates and fails. The system breaks down because the model lacks continuous memory, digital hands to operate tools, and runtime security to execute safely. Writing more detailed prompts or chaining together different language models cannot solve this bottleneck. The failure is architectural. At Google I/O Connect India, an architectural roadmap was introduced to solve this. It relies on a purpose-built infrastructure with 3 pillars. First, advanced agent orchestration. Second, seamless web interoperability. And third, strict runtime security. Handing over direct execution rights to a machine requires a new set of protocols. Developers must adopt these purpose-built standards to make autonomous agents viable. To successfully bridge the gap from a chatbot to an autonomous digital worker, developers must rebuild the digital infrastructure from the ground up. That starts with how we orchestrate the agents themselves. Managing a single AI script is relatively straightforward. Managing a swarm of specialized AI agents, all working simultaneously on different parts of a massive project, is a logistical nightmare. Google's solution is Anti-Gravity 2.0. This is a second-generation local development platform designed to act as the central command hub for multi-agent workflows. This architectural block diagram shows how the hub operates. Instead of forcing one generalized model to handle every task, the Anti-Gravity 2.0 platform dynamically spawns highly specialized sub-agents for the front-end, back-end, and database logic. By working in parallel, these distinct agents process separate data streams simultaneously. This drastically reduces the total development time for a full-stack application. But parallel execution introduces high risk. If the agents do not communicate, they will contradict each other, duplicate work, and ultimately corrupt the application's core logic. To solve this, the stack utilizes a massive shared state, powered by the Gemini model's 1 million token context window. All independent agents continuously feed and pull data from this central pool. Because of this continuous memory bank, the back-end agent knows the exact parameters of the user interface that the front-end agent built just seconds prior. These agents are engineered for true execution. They run compilers, hit external APIs, read terminal outputs, and automatically iterate on their own code if they trigger an error. The platform is also natively multimodal. Agents can ingest visual architecture diagrams, read screenshots of terminal errors, and cross-reference them with complex documentation in real time. Successful orchestration relies on the continuous synchronization of a shared multimodal state. This ensures that independent agents execute and iterate on code without logic conflicts. Internal orchestration handles the local code, but autonomous agents must also be able to navigate and utilize the live web. Historically, developers bridged this gap using screen scraping. This method forces an AI to visually scan a web page and guess where interactive elements, like a login button or search bar, are located. This simulated UI shows why visual guesswork fails. A sweeping scan of a dynamic web application is brittle, slow, and generates a massive cluster of wasted computational tokens. The severe computational cost of this visual scraping method routinely demands upwards of 2,000 tokens spent per single action. Google eliminates the need for visual scanning entirely through the Web Model Context Protocol, or WebMCP. WebMCP is a proposed browser-native standard. It allows websites to expose their functionality to the AI using a structured language it natively understands, represented here by a clean document object model tree. Instead of forcing the AI to guess, the document object model declares hidden structured tags. It defines context for the underlying data and tools for the specific actions the agent is allowed to take, like filtering a pricing tier. Switching to clean schema tags results in a massive efficiency gain. The computational cost drops to between 20 and 100 tokens per action. This protocol also enforces strict privacy constraints. Access to the website's tools is ephemeral and strictly tab-bound. The data is only exposed to your agent while you, the human user, have that specific browser tab open. The moment the tab is closed, the agent loses all access, neutralizing the risk of rogue background actions. By abandoning visual screen scraping in favor of structured DOM interoperability, WebMCP drops computational token costs by 95%. This makes large-scale, autonomous web navigation economically viable. Giving an AI the ability to alter local files and ping external databases creates a massive attack surface. The primary threat vector for autonomous execution comes from prompt injection attacks, where an agent inadvertently ingests malicious instructions from the live web. To neutralize this risk, Google's privacy and security research team introduced Capabilities Security for Agents, known as CAPSEM. Returning to our stack diagram, we see CAPSEM's foundational principle of absolute quarantine. It forces every executing agent node to operate inside a strictly isolated virtual machine sandbox. Under no circumstances can the agent interact directly with the host operating system. The host OS, local credentials, and company network are positioned safely outside the quarantine zone. CAPSEM enforces strict credential isolation. Private API keys and sensitive local data are kept completely out of the agent's reach. The agent can request that an action be performed, but the request hits a firewall on the boundary. The action is verified and triggered on the host side, meaning the agent never actually holds the authentication keys itself. This physical separation enables blast radius containment, the ultimate failsafe for hijacked systems. Consider a scenario where an agent ingests a malicious prompt from the web. The prompt executes, and the agent attempts to spread the infection outward. The isolation ensures the attack stops completely at the virtual machine boundary. The host system and broader company databases remain completely untouched. Because the damage is quarantined, the infected virtual machine is terminated instantly. A fresh, secure container is spun up in seconds, and the workload resumes. By strictly isolating the execution environment, CAPSEM ensures that granting an AI system autonomous terminal and file permissions does not compromise enterprise integrity. The threat of prompt injection is neutralized through blast containment. The novelty phase of artificial intelligence is over. We now have the technical requirements for true executable digital labor. This diagram shows the complete architectural blueprint, the agentic stack. Anti-Gravity 2.0 provides sub-agent orchestration and shared memory for parallel execution. WebMCP provides an efficient protocol for structured web interaction. And CAPSEM provides the runtime security that makes enterprise deployment viable. AI systems can now securely execute complex, collaborative workloads. For engineers and business leaders, this interconnected stack provides the architectural requirements for deploying, scaling, and securing autonomous agents.